Welcome to radar system course. We see few numericals on the radar. A radar operates at a PRF of 1000 hertz pulse repetition frequency. Okay, that is about 1000 hertz with a pulse width with a pulse width with a pulse width of 2 microseconds and at an average power of 100 watt. Find peak power, and duty cycle. Okay, now in this case the given is about a pulse repetition frequency. This one is about a given. We have a pulse repetition frequency of 1000 hertz is given. Then a pulse width is about a given about a 2 microsecond. Then average power is about given, that is about a 100 watt. Okay, so now from this we are supposed to find out, so what will be the peak power and the duty cycle. So now what will be the peak power? Peak power is nothing but the ratio of the average power. Okay, you can say that a peak power now is equal to ratio of the average power. Okay, so whatever the average power we have divided by what will be the pulse width, that is PRA, pulse repetition. Now in this case, pulse average power, that is about 100 watt here. We have a pulse width of what? A 2 microsecond, for minus 6 now, plus, sorry, six into we have a 1000. Okay, so now we can find out what will be the peak average power. So if we solve it, so we have 10 to the power minus 6 there, 1 by, okay, so this will be your 5 now. Okay, so this one supposed to be goes up, that's about a 6. We have 3 removed, okay, and about a 50k. We can say that the peak power, that is about a 50k. Now the duty cycle. Duty cycle is nothing but what? A peak average power. Okay, ratio, we can say that average power to the peak power. So we'll get that whatever the average power we have, that's about 100 watt divided by, we can say that we got that 50k here. Okay, so we can find out that is average power. Okay, so we will get that a duty cycle from this. Okay, so this one is about it, a 2 into 10 to the power minus. Okay, so that is about you what you can say that a duty cycle. Okay, so this is about a duty cycle, that is about it 2 into 10 to the power minus. So even if sometimes what happen, there will be the given conditions are instead of a peak power and average power both are given, and then need to find out the duty cycle, okay, or a pulse. That's about, we can see that pulse repetition time. So pulse repetition time, even if supposed to be you find out the pulse repetition time, so that pulse repetition time, even it's not mentioned, the pulse repetition time is nothing but what? Pulse repetition frequency. Okay, 1 by PRF. 1 by PRF. What is the PRF here? Pulse repetition frequency, that is about 1000. We will get that it is about what? 10 to the power minus 3. Okay, so we can find out from this it is about a pulse repetition frequency is about a 1 to the 10 to the power minus. Okay, that is about your, you can say that from this we can say that it's about a 1 millisecond. Okay, that's about a pulse repetition time. Okay, so we can calculate also a pulse repetition time from this because a duty cycle and everything is a given. Next is about another, we will go for another one. We see the few numericals and just conclude here regarding the radar and all. If next now, if stationary CW radar if stationary CW radar transmits transmits at a frequency transmits at a frequency of 6 gigahertz. Okay, that's about your transmitting. Find Doppler frequency find Doppler frequency due to a target moving with a radial velocity of 200 kilometer per. Okay, so now what will be the radial velocity? Okay, that this one is given. Find the Doppler frequency. Okay, our aim is about to find out the Doppler frequency. The transmitting frequency is given, that is about a 6 gigahertz. So we should know that. So what will be the Doppler frequency? The Doppler frequency is nothing but what? What will be the radial velocity? Okay, that is about radial velocity VR. That is this one is given about 200 kilometers per over here. And what will be the A frequency? So lambda is equal to what? Lambda is nothing but what? C by F. Transmitting frequency is about a 6 gigahertz. So 3 to 10 to the power, we can have the velocity, that is 6 into 10 to the power 9. Okay, gigahertz. So what will be the lambda? Lambda is equal to 0.05 meter. If we put that lambda here, it's about 0.05 meter. That is about FD is equal to twice VR. 2 into VR. VR is equal to what? It's 200 kilometer per hour. Okay. And this one velocity, if we have seen that it is in terms of what? A meter per second. Your lambda is again in terms of a meter per second. Now we need to convert that velocity in terms of a meter per second. So VR is equal to 200 kilometer per hour is equal to 55 meter per second. If you put that Ft is equal to 2 into VR divided by lambda, that is 2 into 55 divided by 0.05. So we will get that Fd is equal to 2.2 kilohertz. That is about a Doppler frequency. Okay, this one is about a Doppler frequency. Okay, so we should know that. So what will be the a Doppler frequency shift for the given particular Doppler, that for the velocity. Okay, next, see that another one. Continue here again. Next one. Okay, so now a radar signal takes radar signal takes a 200 microsecond to travel towards the target, towards the target and right that and back, find the range of the target, find the range of the target. Now we know that a radar range is equal to what will be the velocity here, what will be the time here divided by 2. So that c is equal to what, 8 times for 8, and what will be the time here, it is in a 200 microsecond. You can say that we need to write in terms of it 200 seconds. Okay, 200 10 to power minus second divided by 2. That will give you the range of the radar is about a 30 kilometers. This way we will get that range of the radar, that's about a 30 kilometers. So from this we can find out, so what will be the range, okay, with the help of what will be the that travel times we require. Okay, next one, the radar receiver a radar receiver has an radar receiver has an IF bandwidth IF bandwidth of 3 megahertz, IF bandwidth of a 3 megahertz, and a noise figure of 9 dB. Find the minimum receivable signal, or we can say that a detectable signal. Detectable signal. Okay. right? What will be the minimum detectable signal? So now in this case, we need to know about what will be the minimum detectable signal. Okay, so let's say that minimum detectable signal MDS. Okay, minimum detectable. So minimum detectable signal, that is depending upon that what will be the noise figure, what will be the bandwidth here. So in that case, it is about ATA here, then the bandwidth now, then F minus 1. Okay, that's about a noise figure. So from this, we can write here what will be the minimum detectable signal. Okay, so if you know that what will be the Boltzmann constant value K, then a absolute temperature, okay, that is about a 290 K, then F noise figure is given, that is about a 9. So we can write here K is Boltzmann's constant 1.38 into 10 to the power minus 23 into your temperature, that's about a 290 now, okay, 290 Kelvin, into bandwidth is about 3 megahertz 10 to the power 6, okay, into 9, that's about 9 dB. Okay, so we can, that is about a noise. Okay, so we have noise figure is given, that's about a 9 dB. So that dB is to be converted. So F is equal to what? It is about a 9 dB. So it is to be converted in the form of a number. So we are supposed to be taken anti-log of 9. So that is about anti-log of what? 9 by 10. That will give us a 7.9. So here we can write 7.94 7.94 minus. Okay, so we can say that this is about a K, in the about a 290 Kelvin, this is about your frequency, that's bandwidth here, and this is about a 7.94 minus 1. This factor is about a noise figure that's converted in terms of the number. So from this, we'll get that a minimum detectable signal, if you solve it, we'll get that minimum detectable signal is about a 834 into 10 to the power, okay, 50. That's why we can 12, sorry. Okay, so we have a 6, this one. Okay, so we can calculate here, so we can write, stop that. Okay, so this is about what we can say that minimum detectable. Okay, this way we can find out that, so what will be the minimum detectable signal. Okay, so now next another one, we will go ahead. Okay, so next one more numerical we'll see here. A radar operates at 10 gigahertz. Radar operates at a 10 gigahertz and peak power and a peak power of 500 kilowatt and a peak power of a 500 kilowatt. Its minimum receivable power, its minimum receivable power is 0.1 watt. Okay, just like we used earlier, that is 10 to the power minus 12. Its antenna has a capture area. The antenna has a capture area of 5 square meter. Okay, 5 square meter. And the radar cross section and the radar cross section of the target, radar cross section of the target is 20 square meter. Find maximum range. Find maximum range of radar. Okay. So now we are supposed to consider here. So what will be the maximum range of a radar? R max is equal to, at maximum range of radar is equal to your power. Okay, so what we supposed to be get the peak power there. Okay, that's about peak power here into, that is area. Okay, so what we are getting, that capture area there, AC. Okay, so this is about a capture area, peak power, capture area into what we supposed to get, that a radar cross section of the target, that is about a sigma. Okay, so this is about a sigma is about a 20 square. And then we have 4 pi lambda square, and then a minimum detectable raised to 1 by. So if you put that, what will be the peak power here? Peak power right now, if you consider here, it is nothing but what? A 500 kilowatt. So 500 into 10 to the power 5. Okay. So now 500 into 10 to the power, that is about a 3, that is about kilowatt, into 5, that is about a capture area is about a 5 here, plus area square. Okay, so that's right. A 5 square. Okay, so we can say that a 5 square into what will the cross section, radar cross section of the target, that is about 20 square meter. Okay, so divided by 4 pi lambda. Lambda is equal to what? C by f. F is equal to what? A 10 gigahertz. Okay, so we can calculate that lambda is equal to C by f. Okay, lambda is equal to C by f equal to C by, that is about 10 to the power 10 to 9. Okay, so from this we will get the lambda. It is about a 0.03. Okay, so 0.03. We can put that the values of a lambda is equal to 0.003 meter into what is the minimum detectable signal, that is about a 0.1 to 10 to the power minus 1 raised to 1. So if you solve it, okay, if you solve this one, so you will get that the maximum range of the radar, that is about a 685 kilo. Okay, that is about a maximum range of radar. Okay, so that's all about what we have seen here, the maximum range, unambiguous range there. Okay, uh, what will be the minimum detectable signal, pulse repetition frequency, pulse repetition time that we have seen. Okay, so this with this we stop there. These are the numericals for model 1 and model 2. So thank you all. Thank you.